Hello, and in this video, I'm going to be discussing a new theme, areas of regions enclosed by curves. Now, you do need to know integration. I've covered integration, right? You should know how to evaluate the definite integral using the second fundamental theorem of calculus, right? And assuming that you do in fact know how to do this, then we can move on now to more complicated curves, right? Previously, we learned how to integrate, finding the signed area, giving it orientation and all those things. Now we're going to go back and start studying what integrating can do. Allows us to find areas of curves, right? And the main thing is you have to understand that not every curve is going to be simple. It can be enclosed in many different ways. This region, for example, which we'll look at right here, um, it's enclosed by the graphs f and g, and it's bounded between x equals a and x equals b, right? How would we find this area? I mean, this is kind of weird, but it has some pretty important real life applications, right? Not every figure is a triangle or a square or a circle. As long as you can model it, calculus gives you the answer. So what we're going to do is that we're going to take these blue line segments and we're going to translate them here, all right? And this is our function, which takes these vertical lengths, right, and plots them here as a function. Notice that C when the functions intersect, and at D when the functions intersect, we have zeros. Now, this function is sorry, not the positive area, it's the absolute value of f minus g. That's what these vertical line segments are, which are the blue ones, right? You might want to look at them side to side to see they are the same graph, just that to the left is f and g, and to the right is f, the absolute value f minus g. Now, if we integrate the vertical lengths, right? What we should get is the positive area enclosed by this region. Well, what do I mean, right? Well, we have maybe like you might want to think, oh yeah, we have this change delta x, right? And we can, use Riemann integration, and you can think of it like that. But ultimately, you're just gonna have to realize what we're doing is that we're taking this difference, this vertical length, and when we integrate it, it would be the same thing as trying to find the area of these infinitely many rectangles contained within our region. All right. But we can definitely integrate this. This we know how to take a standard integral. So that's how we're going to compute this area by transforming it into this. Category one has to do with the x-axis. Region R is composed of all points x comma y such that x is between a and b and y is between, um, obviously it has to be between f and g at any point. That's a bit more complicated, but you just need to know kind of what your region looks like. And that's obvious, hopefully. And VL, which is vertical length of x, right, at any point, is the length of the vertical segment at x, which is to say the vertical line of x is just the absolute value of f of x minus g of x. And of course, assuming f and g are Riemann integrable, this function itself is Riemann integrable on the interval. We define the positive area of R to be just the integral from a to b of the vertical line segment, which is also the integral from a to b of f minus g. We note when f is greater than g, when f is above g, right, f minus g is positive, and when g is above f, g minus f is positive, right? So we know now how to take absolute value. Whenever they intersect, we need to switch the order of the inside the absolute value. And that's for category one, right? For category two is when we talk about relations that are not necessarily functions. I mean, we can still do this for functions, but who have inverses who are. Now, the key thing here is that the inverse, or you look at it from the other way, right, is the function. Otherwise, we can't apply this. This is the big thing. If we have this example like right here, we note that from this perspective, they're not functions. They don't pass the vertical line test. G specifically, I'm drawing, that's not very vertical. This is a vertical line, and also this is a vertical line, so it's definitely not a function, right? But if we flip our perspective and we look at it, maybe you want to twist your head to the right, um, it actually is a function from the y-axis perspective. So region R is the same exact region, right? But we, instead of taking vertical line segments, we take horizontal line segments, and our points are x comma y, which is f of y, because x is a function of y, if we can express it like that, comma y, and g of y comma y. And we define the horizontal line, the horizontal line of y as the horizontal segment between f and g of y. That is, the horizontal line of y is just the absolute value of g of y minus f of y, which is again Riemann integrable. And we define this positive area in respect to the y-axis now as the integral of the horizontal length of y dy. So we have the vertical length of x dx and the horizontal line of y dy. And I'm not going to explain kind of the whole transformation up here because I explained it. It's the same exact idea here, integrating with respect to the y-axis, these horizontal lines, right? Now here's an example, all right? And this is straight from me. I made this myself, created the functions, right? So a 2D cross-section of a beat can be modeled by the region enclosed by the two lines y equals 2x and y equals negative 2 over 81 x cubed plus 2 over 3x plus 3 on the interval 0 less than or equal to x less than or equal to approximately 4.08304. The graphs for the lines are shown below. So right here, I have the graph. Take a look at it. I'm not going to scroll down because there I have the answer. Um, this is kind of what the beak looks like. It's the yellow region, right? Hopefully it kind of looks like a 2D cross-section of a beak. And I showed you the point of intersection. Part A asks, write, but do not evaluate an integral expression of the area of the beak using the x-axis as your axis of integration, right? So we have y and we have our two functions. We'll name the first one y equals 2x f of x, and the second one as g of x. Now, which one's on top? The red one, which is g of x, is on top. So the absolute value of f of x minus g of x is just g of x minus f of x, right? That's what our vertical line segment is. The vertical line of x is g minus f. So how do we do that? Well, the key thing here to note is what's it called? Um, mm, Here, F is um sorry, l- less than G, right? That's the big thing. F is below G for 0 less than or equal to x, less than or equal to 4.08304. So the vertical line is just this whole thing, right? Obviously with a minus since it's less. So definitely keep that in mind as a minus. So this vertical line segment, you just put the signs, but that's not the point. The point is that you understand how to get the vertical length and you know how to integrate this vertical length, right? So where do we go? We go from our original point x equals 0 to x equals 4.08304, right? And we integrate the absolute value of f minus g, which in this case is g minus f, right? And I just wrote this negative here because honestly, this is easier to integrate. Now, I'm not going to ask you to integrate. You should know how to do that. That's why I said you should know how to. But I'm not going to do that, right? Here's another example. Find the area of the region enclosed by the graphs, the curves, y equals x squared and y equals 3x. Sorry, 3 square root of x, using category 1 and 2. F of x equals x squared, g of x equals 3 root x. First, we need to find points of intersection, all right? How do we do that? System of equations, and solve, and algebra, and you get x equals 0 or x equals the cube root of 9. Now, the output of the cube root of 9 is cube root of 81, right? So this is our point of intersection here. The other point of intersection, which I didn't write, but it's more obvious, it's just the origin, 0, comma 0. So what do we note? We note that 3 root x is above x squared. This is due to the fact that first, I mean, you can justify this in many ways. You could take a test value and see which one's above. But you could use algebra. But in this case, I think the easiest way is that 3 root x is concave down and x squared is concave up. So if we draw a secant line from the points of intersection by our definition of concavity, I already discussed, 3 root x is above its secant lines and x squared is below its secant lines. So of course, uh, what we call g of x has to be above f of x, right? Which is to say that, um, and also, again, I don't know why I did that, but which is to say that a vertical line is g of x minus f of x, which is 3 root x minus x squared, right? So our area is just the integral from our x coordinate 0 to our second x coordinate through cubed root of 9 of the vertical length of x, which we said was 3 root x minus x squared. dx. dx tells us, oh, the x-axis is our axis of integration. If we wanted to do category 2 with our y-axis, now we need first the inverse functions, right? So y equals x squared implies the square root, sorry, the absolute value of x is equal to the square root of y, but we know x is greater than or equal to 0, right? We're focusing on the first quadrant. So our inverse function f of y is equal to the square root of y. For the second one, again, it should be more obvious. G of y, which is our inverse, right? X is equal to x, is y squared over 9. So here we need to focus at the on in respect to the y-axis, right? So this point is x comma y, which is the square root of y comma y, and this point is again x comma y, which is y squared over 9 comma y. Now, which one is above which one? So the square root of y is greater than y squared over 9, right? You should be able to see that because it's to the right, so it's greater. So we're going to say that our horizontal length is the square root of y minus y squared over 9. And remember, we're integrating this horizontal length from 0 to our y, which in this case is the cube root of 81. And we note here that we're computing the same area in two different ways. So this result up here should just be equal to this result down here, assuming we integrate it. Now from the 2024 AP Calc FRQ, right? Question 6. The functions f and g are defined by f is equal to x squared plus 2 and g is equal to x squared minus 2x. They give the graph, and this one is modified. Let R be the region bounded by the graphs f and g from 0 to 2, right? And evaluate, right? This one originally said right, but do not evaluate, right? And evaluate an integral expression that gives the area of the region R. All right, so we're gonna use category 1, right? We're gonna take vertical lines, right? And we're gonna say our vertical line of x is equal to, right? Here we have f of x is greater than g of x. So our absolute value of f of x minus g of x is just gonna be f of x, x squared plus 2 minus g of x. And notice conveniently, this cancels out. We just get 2x plus 2, right? And we are integrating our vertical lines from 0 to 2 in respect to x. Oh, okay, well, I mean, if you know how to evaluate an integral, it should become apparent that this integral is a piece of cake. And we'll even factor out a 2, and we'll do x squared over 2 plus x from 2 to 0, right? And this is equal to 2 times, we're not going to consider the 0 because we're subtracting by 0 squared over 2 plus 0. So we're subtracting by 0. So evaluating the 2, we get 2 squared over 2, 4 over 2, 2 plus 2, and I said minus 0. So we should just get 8 as our answer. And for 2022, question 2, so this is the calculator problem, so get your calculator out and try this yourself. Let f and g be the functions defined by f of x's natural log of x plus 3, right? So we're going to write f of x is the natural log of x plus 3, and our calculators define it. And our second function, b of x, is what x to the power of 4 plus 2x to the power of 3. We're done there. Now, in the figure above, they intersect what? X equals -2 and x equals b. So we're looking for this other intersection point. So we're gonna solve for when we're going to solve for when f of x is equal to g of x, right? So we're going to write f of x is equal to g of x. We're gonna solve it. And what do we get in our calculator, right? Now, of course, we know that there are two solutions. That is pretty obvious, but we only care about the second solution, which is x is equal to 0.78197, 5 decimal places. So this is B. This is B. If you want to find the area of the region enclosed, we can take vertical length. So clearly, um, you want to look at which one's above. I'm just going to take a test value, 0, all right? F of 0, compare that to G of 0, all right? And G of 0, so you get F of 0, obviously, is 1 point something something, and G of 0 is just 0. So, okay, F is greater than G, and we know this is true throughout the entire, um, throughout the entire graph, F is above G. That means that our vertical lines are just going to be the absolute value of f minus g, which is just f minus g, which is ln x plus 3 minus x to the fourth minus 2x cubed. So the area is just from -2 to b, which we said was 0.78197 f of x minus g of x dx. And this has now become a calculator problem, right? We just plug in -2, 0.78197, right? F of x minus g of x, and then dx, and we're done. We get the area should be approximately 3.60354. And that's it. That's our FRQ done, right? So College Board doesn't tend to go too overboard. These problems are easy, but you need to know this because when we get to volumes, cross sections, and squares, and then rotating along axes, it's really important to have these fundamentals down, right? And although the questions they'll ask are going to be super easy, they'll give you the graphs and everything, right? You really should know this is the exception, right? This is not what every question looks like, and there have been hard questions in the past. Do I expect there to continue to be hard questions? No, not really. It got watered down a lot. It's really easy, whatever, whatever. But I mean, that's enough, right? So good luck studying, and if you have any recommendations for what video I should make next, because honestly, I'm not sure yet. Definitely let me know, and I'll continue working on my review videos so that you guys can review that. All right, so good luck.